Hi, I'm Peyton, and today I'm going to be explaining Lab 3, which is the magnetic field of a bar magnet. So, the objective of this lab was to observe how distance affects the magnetic field, look at this through a computational model, and find the magnetic moment of a bar magnet. The results that I found was actually that mu is 5.073. I found that through calculations, and then through the experiment, I found that n is negative 2.465. So there are some important concepts to understand going into this lab, which is the Biot-Savart law, the distance dependence formula, and then this one that is actually derived. The third one is going to be derived from the second one. All three of these are going to be incredibly important when we're calculating later, because then we can plug in important values to GlowScript. So there are some things that we're going to be assuming. We're going to assume that the bar magnet is acting like a magnetic dipole. This is really helpful because bar magnets typically are like this anyways, but I actually drew a model here of what it would look like, the magnetic field of this bar magnet, and so this will hold true later. So for the experiment, we started by locating the magnetometer chip in a cell phone. Originally we used mine, but it wasn't working, so we had to use someone else's phone. But we found the magnetic north by rotating the phone to find Earth's magnetic field. In Atlanta, it should be roughly 49 microteslas, and we did this until the exponent was 0. So it was also really important that we made sure no magnetic objects were around, because this can mess up the data, but sadly we were in the physics room, which is everything is magnetic. Well, not everything, but a lot of things are. So this definitely could have messed some things up. But the bulk of the experiment was when we found the on-axis distance using a meter stick of different magnetic field values. So basically, we measured the distance from the magnet to the chip until we reached a magnetic field X component of a particular value that we were needed to find. The system in this case is the magnet, the surroundings would be everything else around. So here is the data that I was referencing. For instance, if we had to find the magnetic field of the 20, 70, 120, we would just have to find the distance that would yield that result. And Excel would linearize this for us, all of this results, so that we can then get this graph that has y equals negative 2.465x minus 13.801, because this is what we need to calculate the next thing. So on GlowScript, there is a section where it's like mu mag equals. You actually have to calculate this before you can type that in, using all three of these formulas. So we can manipulate what we just found. Instead of it being y equals negative 2.465x minus 13.801, we can change it to be y equals negative 13.801 minus 2.465x to match the formula above. But we need k, right? But we don't want the natural log of k. We want the inverse of that. So what we're going to do is we're going to do e to the power of negative 13.801. That's how we're going to get k, because here we're going to basically be equaling the distance dependence formula to the Biot-Savart law. And we already know r, we know n, because as you can see up there, n is going to be negative 2.465. That matches the formula above. We know what k is. We can set those equal to each other, and we can get mu. Then once we know mu, we can plug that one into GlowScript right there where it says mu mag. Then down there where it says definition and then dipole, B, I typed in R mag, R hat, and then B, which is the magnetic field formula. And then all of these observation locations are going to be important for the model. But here is where I have all of my arrows, both on the perpendicular axis and then just for the 45-degree. So all of these are the arrows that we're going to see in the model, which is right here. This model looks pretty accurate, looks pretty good. We have all of these different values of these different axes, and but as we can see, the net magnetic field of my experimental value is different from the net magnetic field of my computational value. This is because there are outside forces, like I was talking about, like the magnetic objects around that could have skewed the data when I was doing it experimentally, but also just have to keep in mind that computationally it's always going to be a bit more accurate. But some error, we might not have found the exact location of the phone's magnetometer, which then could have messed up the distance values we found later in the experiment. The magnetic objects lying around, as I've explained multiple times, but we also, the magnetometer reading might not have matched exactly with the Earth's magnetic field. However, the assumption we made about the magnet being a magnetic dipole makes for incredibly accurate results, because a bar magnet's magnetic field is similar to a magnetic dipole, so that was a good assumption that we made. Discussion. What if you hadn't oriented your experiment to compensate for magnetic north and instead laid out your meter stick at some intermediate angle with respect to Earth's magnetic field? How would your results have changed? So the data collected would have not been very accurate. This is because the Earth's magnetic field would have interfered with what I was reading on my phone's magnetometer, which yields results that are not quite precise. So now, what if you were to stick two identical magnets together end to end and run the experiment again? How would you expect your measurements to differ? So the direction of the magnetic field would actually remain unchanged. However, the magnitude would increase, likely double, because there was another magnet present, meaning that there's more strength. That is all. Thank you so much for joining.